This is the first video I'm doing of all of my individual topic videos for MA 266 and 265. This is phase plan identification for MA 266. And there's a reason I'm choosing it as the first one. It's probably the simplest of all the 266 topics to run through really quickly. So we have 5 questions to go through. Consider the system x prime equals ax. Find all the values of alpha such that the origin is an asymptotically unstable spiral point. So we know that the characteristics of our phase plane are completely determined by our eigenvalues. So if our eigenvalues are positive and real, we are going to get a source node where any path will be forced away from the origin as time goes on. If our eigenvalues are negative and real, everything will come in towards the origin. But if we have those same positive and negative real parts, but then an imaginary part added onto that, an imaginary conjugate pair, then we will get either a spiral source or a spiral sink. And here what they're saying for an asymptotically unstable spiral point, well, asymptotically unstable, meaning you can think of the origin as kind of a mountain peak. As long as you don't start exactly on that origin, you're going to flow off down the side of the mountain away from the origin as time goes on. So we are looking for a positive real part of our eigenvalue, and then a conjugate pair for our imaginary part. And so solving for that, we're going to be solving the determinant of A, this matrix right here, minus lambda I. So that means solving 0 minus lambda, alpha minus lambda, plus 16 is equal to 0. This is lambda squared minus alpha lambda plus 16 is equal to 0. And solving this using the quadratic formula, we will have negative b, so positive alpha over 2 plus or minus the square root of b squared, so alpha squared minus 4ac minus 64, all divided by 2. And we'll see that as long as our alpha value is positive, we will get this a positive real part here. And as long as alpha is less than 8, we will end up with a imaginary solution here, because anything between 0 and 8 squared minus 64 will give us a negative number under that root. So alpha must be between 0 and 8. 18, let's find all the values of k for which the solutions of the system x prime equals ax spiral into the origin as t approaches infinity. So this is exactly the opposite of what we were looking for here, in that this you could rewrite to say that we're trying to find an asymptotically stable node. So this is almost like a trench or I don't know, a big hole in the ground, an inverted mountain, where as long as you don't start at the origin, any path, any initial values will eventually take you to the origin in a kind of spiraling whirlpool of a path. So we are looking for a negative real part and a conjugate pair imaginary part. So solving the determinant of a minus lambda I equals 0, we have negative 2 minus lambda times 0 minus lambda plus k is equal to 0, or lambda squared plus 2 lambda plus k is equal to 0. And we will have negative b over 2, so that's negative 1 plus or minus the square root of b squared, so 4 minus 4 times a times c, all divided by 2. And in order for this second bit to be imaginary, we need 4k to be greater than 4. So as long as k is greater than 1, so our answer is B, we'll have a negative value in here, and we'll get the imaginary conjugate pair that we're looking for. This is a much easier one. We're just trying to identify the phase portrait of this system. So like we normally do, -2 minus lambda minus 4 minus lambda minus 3 is equal to 0, or lambda squared plus 6 lambda plus 8 minus 3 is plus 5 is equal to 0. This will factor to lambda plus 5, lambda plus 1 is equal to 0, and this gives us lambda equals -5 and -1. When our eigenvalues are like this, both negative, we know that we are not getting any spiral behavior. We also know that we're not getting a saddle point, because that occurs when we have one positive and one negative eigenvalue. In fact, this is just going to be an asymptotically stable node where everything, all initial conditions, will flow in radially towards the origin as time goes on. 19, the phase portrait of this system, we're trying to identify the origin just like normal. So -3 minus lambda minus 1 minus lambda plus 2 is equal to 0. Lambda squared plus 4 lambda plus 3 plus 2 is plus 5 is equal to 0. So let's see, does this factor? This does not factor. So -b over 2a will give us -2 plus or minus the square root of b squared. 16 minus 4ac is minus 20, so this will give us 2i over 2. So -2 plus or minus I, and we saw earlier that when we have a negative real value and a conjugate imaginary pair here, we will end up with an asymptotically stable spiral point. As just like before, everything will be flowing in towards the origin due to the real part, but the imaginary part will be causing some rotation along the way. And finally, we know what to do here. We're solving 1 minus lambda times 1 minus lambda minus 3 alpha is equal to 0. Lambda squared minus 2 lambda plus 1 minus 3 alpha is equal to 0. Setting up our quadratic equation, quadratic formula, negative b, so 2 over 2a plus or minus the square root of b squared, 4 minus 4 plus 12 alpha, there's our 4ac, all over 2. So we get 1 here, and just simplifying a little bit more, we have 12 alpha under here. We can bring this 2 up into the root by squaring it. So we'll have 12 divided by 4. That will give us 3 alpha in there. And then we're looking for the values of alpha such that the origin is a saddle point in the phase plane. Well, we said that a saddle point occurs when we have one positive and one negative eigenvalue. And that will be true. We need a negative value somehow on this negative side of our plus minus, if and only if this evaluates to some value greater than 1. And I hope that's easy to see. If we have 4 in here, this will give us a negative value because it's able to subtract more than 1 from this 1, so we end up in the negative. So this alpha just has to be bigger than 1/3. As long as it's bigger than 1/3, we will end up in the negatives and in the positives. I feel like I'm putting way too much effort into explaining that a little bit, but hopefully you can see that a is our correct answer. And with that, we're done.